So I would like to thank the organizing committee for the opportunity to show the results of this work. This work had been conducted during the 4.5 years that I've been a postdoc in Porto Alegre. So we are presenting here the experiments that we performed during 21 beam times and recorded more than 13,000 spectra. So how do you analyze so many spectra? So you call some students, and this presentation here will show you the results of the work of Gabriel Onzi with the simulation code. So we need to build up this code to interpret the results that we are observing when we are using continuous source of primary ions. We also developed a way to record the flux and then compare time-dependent spectra. So how spectra that is acquired given an elapsed time as the flux of ions is impinging on the sample. This is the work of Lucas Batu with polymers, and this is the work of Beatriz Davila with ionic crystals. So to begin with, and to be very short in the motivation and introduction parts, I would just say that we have, as many members of this community, the interest of developing total ion beam analysis, which is concomitant elemental and molecular characterization. In our lab, as in many labs, we are trying to use the secondary ion mass spectrometry that is enhanced by the use of mega electron volt primary ions. So there is electronic sputtering, of course. I won't tell anything about it. But the ionization is softer than when we compared electronic sputtering to collisional sputtering. If you are watching the presentations about secondary neutrals mass spectrometry, you will know that perhaps the ionization is not that soft. And this is some of the results that we will show here. When we use such high fluences of ions to do the measurements, we are indeed changing the spectra very fast. And we are breaking up the molecules into, let's say, relatively low fragments. But then, of course, this is our motivation. We would like to go as much as possible to the highest energy deposition that we can do in our lab. So we have a Tandetron system. The SIMS beam line is 30 degrees from the switching magnets. This makes the energy loss, the maximum energy loss that we can achieve in a relatively medium mass, because low mass ions won't accelerate too much, so the energy deposition will be low. And high mass ions, if they have too much energy, they won't bend to this beam line. So what we see in our beam line, that we have an optimal energy deposition around silicon and chlorine. This is some elements that we have very reasonably stable sources. So this is our motivation to use cup, chlorine, and in one experiment, silicon. We have been developing as well in other branches of our, in other beam lines of our laboratory, the relation, for instance, of chlorine and X-ray production cross-section. So we are engaged in trying to extract the best of our system. So that's why we are choosing 6 mega electron volts and chlorine or copper ions. So we have a time of flight reflectron. This is basic kinematics. We can show the results that we can calculate the time of flight in the various sections. So we have the accelerating region. We apply an electric field here, then the ions are accelerated, they get into the mirror, and they are reflected to the detector. So we will consider all of this when we are trying to simulate our spectra to understand a little better what we are observing. So triggering is always a matter of what we are trying to do with mass spectrometry. You have several possibilities, of course, but as we don't have a pulsed ion source, we cannot use techniques as the delay time and so on. But I put it here to compare that in fact, the delay time, we can use delay extraction to measure metastable ions, has a resolution that is somehow strongly influenced by how this highs of voltage goes. What we are doing in our experiments is using the extraction as the trigger. And the question is, of course, what if the primary beam is continuous? So we do standard stuff as the mass calibration, the second order polynomial feed. This was done with polystyrene. We can calculate the resolution of our systems. Of course, the resolution is not too good because we have this very strong fragmentation of the sample, and this resolution that is somehow influenced by the rise of the voltage, but it's okay. Then we go to our simulations here just to explain a little bit the results that I will show later. We are considering this adiabatic expansion as a Knudsen layer, that is this gaseous material, this sputtering, that is the material that is ejected into the vacuum, is expanding with some velocity distributions. And what we do is basically we assume initially a constant velocity, we generate particles, we integrate by finite element methods our extraction field, then we calculate velocity time relations and apply the mirror effects. This was the first version of the code. The second version, we introduced the sample velocity distribution and some detection efficiency as observed by Gilmore and Sear. And it's quite interesting how this changed the observed emission velocities. So from the results, it's quite interesting that as we have a continuous source of primary ions, as the extraction pulse rises, we will observe a plateau. So we have first a peak that is the same principle and idea of the delay extraction. That's why I talked about this, because this gaseous, let's say like this, molecules and ions, secondary ions that are on top of the sample can be accelerated into our detector. So we have an integration of this moving gas. Then we have a plateau. If the mirror voltage is higher than the extraction field. If you inverse, then we just observe the peak, and we have an exit peak as well. This is for H plus, this is H2 plus. And so we can control by the extractant voltage and interpret the emission and understand a little bit better from which time the secondary ions were emitted. And we see that our calculations reproduce qualitatively generally well the shape of the peaks that we are observing. So if you want to do or not to remove this plateau, it depends on what you are doing. I will show two cases, and one which we want to remove and another which we don't. Within the same code, we can calculate the peaks, and we observe, we make different experiments using the reflect voltage, and then we can use this to calculate actual velocities. This is one goal of our setup. The other one is to use the lens to calculate the radial velocity. This is particularly interesting for organic and polymer films. A point that I told you that is interesting, when we put the efficiency of the system, we see that the shape that was previously Maxwell-Boltzmann distribution turns into a different shape, only a tiny fraction of the emitted ions are detected. And we have a very nice result that we can compare with previous observations of emission velocities. On the other hand,
Igor.
Thank you very much. When we go to book materials, we have a problem. We have a problem of charge up. And what happened basically is that if we acquire an spectrum after the other, you will see this is an experiment for lithium fluoride. You will see that the peak area is diminishing and shifting. And then we could use this shift to calculate this charge up effect. And this is really different when we use an electron gun as a neutralization source. So in this case, what we observe is something like this with the gun on. We basically don't see any shift of the maximum here. With the gun off, we see some kind of saturation that we can calculate the charge accumulation and is in the same order of magnitude of the charge that has been has arrived in the sample. Another experiment that we performed was studying the polymer degradation. In polymers, we don't see that shift, but we see that as we are going for longer times, the area in the peak is diminishing. So we can use this to calculate damage cross-section. And of course, we are changing here from static to dynamic regime. So, and this agrees with the expected radial damage of a few nanometers in polymers. And this is indeed very nice because we can record one spectrum in 10 seconds or even 1 second. And this was the program that we did with an Arduino to record the different experiments. So in this case, for instance, there will be 600 expected. So this is a different experiments performed. This is how we calculate the flux and then convert to fluence. But this is the overview that I can give you here in the 15 minutes that I have. I will go to my summary, and I hope I had shown you that yes, we can perform SIMS with continuous beams. The advantage of performing this is that when you do some ERDA or ERDA or even Rutherford backscattering analysis, you need a longer exposition. You need a very high fluence in principle compared to what you need to do mass spectrometry. So it's interesting to see this degradation. You can even see how the samples change during the experiments. In the case of insulators, there was the observation of discharge up effect. In the case of polymers, we can evaluate damage cross-sections. As an outlook, we would like to perform more realistic simulations. So we are integrating a little bit better the field, the extraction field, and then we want to do it three-dimensionally as should be required by the system. So that's what I have to talk to you about our beamline in Porto Alegre, and I thank you very much for your attention.